Good day and welcome to this presentation on Thermosiphon heat exchangers. My name is Sharif Panamariam, presenting on behalf of Group 32. This presentation is about Thermosiphon heat exchangers and how the first law of thermodynamics is applied to it. Without further ado, let's dive into the video. So we first start with a brief introduction about thermosiphon heat exchangers. Then we talk about the working principles of thermosiphon heat exchangers. The next thing we'd want to discuss is the types of thermosiphon systems and how the first law of thermodynamics is applied. This then brings us to the conclusion on this topic. Now, we'd like to talk about the general applications in industry and engineering. In the world of electronics, it is used to remove heat from high-power electronic components like CPUs, GPUs, and power amplifiers. When we come to solar thermal systems, it's used to cool machinery components like turbine blades, transformers, and internal combustion engines. In the waste heat recovery system, is used to recover heat from industrial processes by transferring it to a secondary fluid loop. On this slide, we would like to talk about the working principles of thermosiphon heat exchangers, and here are the four basic components of the thermosiphon. We have the evaporator. As you can see, there's a picture of the evaporator displayed on the slide. The evaporator is where the refrigerant or process fluid absorbs heat from the surrounding fluid. Then another important component of the thermosiphon heat exchanger is the condenser, where the refrigerant or process fluid releases heat to the surrounding fluids. The next component, which is very essential to the functioning of thermosiphon heat exchangers, is the downcomer. Downcomer is a vertical pipe that connects the condenser to the evaporator. And last but not the least, we have the riser. The riser is basically a vertical pipe that connects the evaporator to the condenser. The four images displayed on this slide are the components of the thermosiphon heat exchangers. We now want to move on to discuss the stages that come together to complete the operation of a thermosiphon exchanger. The first stage is the heat absorption stage. We move on to the vaporization stage. Next is the heat rejection stage, and finally the condensation stage. The stages are repeated to complete the operation of a thermosiphon exchanger. To bring more light to this, a refrigerant absorbs heat from surroundings, causing its temperature and pressure to increase. The fluid then vaporizes and rises through the riser due to low density. Then, temperature and pressure is caused to decrease when fluid in the condenser releases heat to the surroundings. Due to high density relative to the surrounding fluid, refrigerant fluid condenses and falls through the downcomer. These stages are then repeated to complete the operation of a thermosiphon. Now, thermosiphons can be classified into several types based on their configuration, application, and operating principle. We would want to discuss 8 common types of thermosiphon systems. The first one is a closed-loop thermosiphon. A closed-loop thermosiphon system is a sealed system where the fluid circulates continuously between the evaporator and condenser without any external interference. It works more or less like a closed system. The second type of thermosiphon heat exchangers we'd like to look at is an open loop thermosiphon. An open loop thermosiphon is the opposite of a closed loop thermosiphon because an open loop thermosiphon is not sealed and the fluid is exposed to the atmosphere. This is often used in solar water heat pumps. Then another type of thermosiphon we have is a two-phase thermosiphon. A two-phase thermosiphon system uses a mixture of liquid and vapor phases to transfer heat. This type of system is commonly used in refrigeration and air conditioning systems. The fourth type of thermosiphon heat exchanger is a single-phase thermosiphon. This type of thermosiphon uses a single-phase fluid to transfer heat. Is often used in heat recovery systems. Continuing, we want to talk of the gravity assisted thermosiphon. This type of thermosiphon uses gravity to assist the circulation of fluid between the evaporator and condenser. Another type of thermosiphon is a forced convection thermosiphon, which uses a pump or a fan to assist the circulation of the fluid between the evaporator and condenser. Also, we have one called a solar thermosiphon, which uses solar energy, just like the name depicts. It uses solar energy to heat the fluid in the evaporator, which then rises to the condenser to transfer heat. Last but not the least, we have the heat pipe thermosiphon. This type of thermosiphon uses a heat pipe to transfer heat between the evaporator and the condenser. The heat pipes are sealed tubes filled with a flowing fluid that can efficiently transfer heat. It's mostly used in refrigeration, again, air conditioning, heat recovery, and solar energy systems. Now, let's dive into one important aspect of this presentation, which is the application of the first law of thermodynamics to thermosiphon heat exchangers. First, what is the first law of thermodynamics? The first law of thermodynamics simply states that energy can neither be created nor destroyed. Now let's take a look at how this law plays a crucial role in the design, analysis, and optimization of thermosiphon heat exchangers. The first thing we'd want to look at is heat transfer. Now, heat is transferred from hot fluid to cold fluid through the heat exchanger. Also, we'd want to look at work. No work is done on or by the system, as thermosiphon heat exchangers rely on natural convection. In this system, heat transfer and internal energy change is involved. Heat transfer because heat is transferred from the cold fluid to surroundings. Energy change because the fluid changes as it gains or loses heat. Okay. The first law of thermodynamics for a thermosiphon heat exchanger has the mathematical formula of what is on the slide. That is delta E, which is the change in internal energy, is directly proportional, is equal to the Q, which is the heat transfer, and work done. Work done is not seen in the equation because no work is done. So the equation simplifies to just delta T is equal to Q. All in all, thermosiphon heat exchangers and applying the first law of thermodynamics plays a very pivotal role in designing, analysis, and optimization of this device. In conclusion, we've come to realize that thermosiphon heat exchangers offer a reliable, efficient, and cost-effective solution for various industrial and commercial applications. By using the natural convection and applying the first law of thermodynamics, this system eliminates the need for pumps and other mechanical components, reducing maintenance and increasing overall system reliability. This brings me to the end of my presentation on thermosiphon heat exchangers. Thank you.